So now that we've covered how to differentiate with the natural log function, that actually opens up the doors and allows us to finally differentiate certain exponential functions. So consider the function like y is equal to x to the x power. Something like this, we previously didn't have any tools to be able to differentiate something like this. We can't apply the power rule here. That is to say, we can't do something like say that this is x times x raised to the x minus 1 power. It just simply doesn't work that way. So what can we do now? Well, now that we understand about how to differentiate with a natural log function, what we can then do is we can actually take the natural log of both sides. And what this allows us to now do is to differentiate each side and treat this not almost, like it's an implicit derivative. So let's go ahead and differentiate both sides. Let me zoom in on this now here. So if we take the natural log of both sides, if I differentiate the left side, this is going to give me y prime over y. On the right-hand side, before I actually differentiate, let me actually just take this here and rewrite this using log properties. That is to say, move this x to the front, so that this side here is equal to x times the natural log of x. So if I differentiate x times the natural log of x, I can now use the product rule. I can then say the derivative of x is 1 times natural log of x plus x times the derivative of the natural log of x, which is 1 over x. And this cleans up pretty nicely to just the natural log of x plus 1. Okay, so I just differentiated both sides. Now for the left side here, I realize I wrote a y prime there. That shouldn't be there. This should be y prime over y. Apologize for the confusion. And I'm going to isolate my y prime. So I'm going to write y prime here and then multiply all of this here by y. Now my final step is to then substitute what y is. We said y was equal to x squared. So we're going to substitute that back in. Y prime is equal to the natural log of x plus 1 times x to the x squared. And there we go. That is a derivative of y is equal to x to the x power. So just to summarize, I'm going to go ahead and write down those steps here. Here they are. Let me just make them a little smaller so they fit. Here are the steps if you want to go ahead and write that down, just kind of recapping what we did. Okay? So let's try a couple of practice problems with this. So let's go ahead and try something like this problem right over here. Y equals x to the cosine x power. So the first thing I'm going to do is I'm going to take the natural log of both sides. And the natural log of x raised to the cosine x power. And then I'm going to differentiate all of this with respect to x. So the derivative of the left side is going to be y prime over y. And just like I did before, I'm going to move this to the front here. So let me actually just write this. Cosine x times the natural log of x. And then y prime over y is equal to the derivative of all this using the product rule. The derivative of cosine x is negative sine x times natural log of x plus cosine of x times the derivative of the natural log of x, which is 1 over x. So I can just write this as cosine x over x. And there's my derivative on my right side. I'm going to go ahead and isolate my y prime. So I can actually just do this in the previous step. Just multiply both sides here by y. And then I can just write this now as negative sine x, natural log of x, plus cosine x over x. All of this times what y is equal to in terms of x to the cosine x power. Okay? All right, let's try a slightly different problem now. Let's try something where we are going to have to use logarithmic differentiation, but in the context of finding the equation of a tangent line at a specific point. So let's look at number 14 here. So I'm going to find the equation of the tangent line to this implicit equation here at the point 0, 1. So this is an implicit equation that we are going to implicitly differentiate, but we notice since we have a logarithmic function in here, we can then write it as the following. If I take the derivative of all this, which is the first step in order for me to find the equation of the tangent line, I need to know my slope. So I'll need to differentiate all of this. So differentiating this, we know the derivative of x squared is 2x. The derivative of natural log of x plus 1, this is just going to be 1 over x plus 1. The right side, this is going to be 2y times y prime. And the derivative of negative 1 is just 0. So if I write y prime as all of this, and I don't really have to simplify just yet, write this all over 2y. And we don't know necessarily what y is in terms of x, so I can just leave it like that. So here's my implicit derivative. Now I want to evaluate this implicit derivative at the point 0 to 1 to find the slope at that point. So this would be 2 times 0 minus 1 over 0 plus 1, all of that over 2. So this is going to be negative 1 over 2. So this represents my slope. Now I can then write y minus my y value, which is 1, is equal to negative 1/2 times x minus my x value, 0 here. So there's the equation of my tangent line. All right, let's try another one here. Let's try this problem here, number 15. So let's find the domain, the extrema, and points of inflection for this graph here. So again, this is a type of problem that we're familiar with doing. We've done many of these in this course, but we haven't done them yet with a natural log function. So we can first start by finding the extrema. Actually, let's start by finding the domain. That would probably be a good place to start. Let's find the domain of this function here. Well, the domain of x is all real numbers, but the domain of the natural log of x are just values from 0 to infinity, right? Natural log function's domain is 0 to infinity. So we're going to keep that in mind as we start going into the first derivative test now to find the extrema. So let's find f prime. So this derivative is pretty easy. The derivative of x is just 1. The derivative of natural log of x is 1 over x. So here's my derivative. Now, to do the first derivative test, we're going to set my derivative equal to 0. Okay, so 1 over 1, well, 1 minus 1 over x. This becomes 1 over x is equal to 1, and x is equal to 1. Okay, so I'm going to draw my number line now. And on my number line, I've got 1, but I'm also going to consider the open circle 0 here, just to know that that is my boundary. Okay, and if I plug in a value between 0 and 1 into my derivative, I see that this value should be negative. Okay, so if I do something like 1/2, that's 1 minus 2, which is negative. If I plug in something greater than 1, now my fraction becomes smaller than 1, so this is positive. So my function is decreasing to 1, increasing after that. So I can say there's a relative minimum at x is equal to 1 because my derivative is equal to 0 and there's a sign change there. Now, where is my relative minimum? Now I got to plug 1 into my function. The natural log of 1 is just 0. So I can say it's 1. So my relative minimum, let me actually write that. The relative minimum is 1, 1. Okay, so I found my extrema. Now, what about any points of inflection? So now let's look at the second derivative. I'll change my colors for that. F double prime of x. So let's differentiate what we found here. Let's take the derivative of that. The derivative of 1 is just 0. The derivative of 1 over x is 1 over x squared. Now let's set my second derivative equal to 0 to find a possible inflection point. Now, if you take a look at this, there is no value of x such that this would ever be equal to 0. So there are no inflection points. Okay? Specifically, we can say that my second derivative is always positive. So this graph is always concave up. There are no inflection points here. Okay? And if you wanted to confirm that, just go ahead and graph that function. You would see that it would be a graph that looks something like, and this is just a really quick sketch. It's something like this. It's always going to be concave up. Okay. All right. Last problem. Let's take a look at this last one. It's just another practice problem of logarithmic differentiation. So we can say we're going to take the natural log of both sides. And this allows me to rewrite this as such. And now I'm going to take the derivative of all of this. So the derivative of both sides. That's y prime over y. This side over here, I'm going to apply the product rule. 6x times natural log of 5 plus 3x squared minus 1 times the derivative of natural log of 5, which again this is a constant. So all of this is just 0. So we can say y prime is equal to 6x times natural log of 5. Right? That's what all of this simplifies down to, times y. and 6x natural log of 5. We know that y is equal to 5 to the 3x squared minus 1 power. Okay? All right, so hopefully this has been helpful in understanding logarithmic differentiation.